Hi guys, welcome to another episode of Organic Chemistry with me, Nkandu. Today we look at homologous series. So to start with, we need to define what homologous series. And what is homologous series? Homologous series simply refers to a family of organic compounds having the same function group and follows a structural pattern in which each successive member differs in composition by a constant number of atoms. So I'll say it's a family of organic compounds having the same functional group and follows a structural pattern in which each successive member differs in composition by a constant group of atoms. So this is how I easily define organic chemistry. Homologous series. And the examples that we give here are alkanes, alkanos, which is commonly known as alcohols. Then we also have organic acids. We also have esters. So that's the examples that I can easily give for this. So I say we have alkanes, we have alkanos, we have alkanos, we have organic acids, and we have esters. Then one thing that we have to keep in mind is that homologous series is made up of compounds of the similar properties. But the question is, how can we classify a particular organic compound or molecule to fall into a particular homologous series? So that takes us to another concept of us looking at the properties or the characteristics that we use to qualify each particular organic compound to fall into a particular homologous series. Since we said they all have the similar properties, so let's observe some of the properties that homologous series contain. So the first property that we have to understand, and as we observe the homologous series, is that all of the molecules, all of the compounds that fall into a particular homologous series, they can be prepared by the same general formula. So here we're giving an example. We're saying they can be prepared using the same general method. I'll give an example of alkanes. If you consider alkanes as the first homologous series, the question is, how can we prepare alkanes? So we can prepare alkanes and alkenes using the general method we call cracking. So which is a concept that we're going to discuss as we advance. But we are simply saying each members of a particular homologous series can be prepared using the same general method. The easiest one being for alkanes, we can use cracking method, and if you also want to prepare alkenes, we can still use cracking. And from alkenes, we can still go back to prepare an alkane, that is by just the addition of hydrogen to an alkene. For alcohols, we can do fermentation and hydration. So all those alcohols, which is an example from homologous series, we're saying all the alcohols that we have can be prepared either using fermentation or hydration of an alkene. We can prepare an organic acid just by oxidizing a given alcohol. Then the other thing that we have to keep in mind is that all members of the particular homologous series, they show the same chemical properties. Although these chemical properties are saying they vary gradually in reactivity along the series. So, and this comes in because as we move along the series of a particular homologous series, we increase the number of carbon atoms. We also increase the molecular mass. As the molecular mass or the number of carbon atoms increases, there is the gradual change in the way each particular member reacts in a given homologous series. Then we say they also show the gradual change in the physical properties, meaning as you increase the number of carbon atoms, you expect also the physical properties to change gradually. For example, if you look at the homologous series called alkanes, you observe that from the first four members, meaning from 1 to member number 4, you find these guys in gas state. Then from carbon the member number 5 to somewhere about member number 12 to 16, somewhere there, you find them in liquid state. Then from 12 or rather 13 going up, 13 and above, you find these changing slowly into solids. That's why we have the greasy, or that's why I have the Vaseline and petroleum jelly that we talk about. Okay. The other thing that we have to consider here again is that each successful member differs from the preceding one by a methyl group. So when we look at the way each molecule in a given homologous series behave in terms of comparison to the next one or the previous one or the preceding one, you realize to say the only difference that comes in is with the methyl group. So the methyl group, in this case I've said the constant group of atoms, and the constant group of atoms, we're talking about this. If we observe what we have as a methane, CH4, so CH4, which is an alkene, first member of alkenes, and if you observe the second member of alkenes, we have C2H6. So is C2H6. So if you observe the difference here is that here we have one carbon, here we have two carbons. So already the difference between this and that molecule is that carbon there. Then if you observe the difference in terms of the hydrogen atoms, there it's 4, there it's 6. So the difference again is 2. So that's the 2 we're looking at here. If we observe the third one, the third member, we have C3 there and H8. And this means that between this ethane and propane, the difference again is still constant. So you observe it is, that's 2, here it's 3 number of carbons. So the difference again is just one carbon atom, so that's still constant. And the hydrogens, they are 8, and here they are 6, and here they are 8. And this the difference also between this and that one is also the 2 atoms of hydrogen. So that's what we say when we say each successive member of a particular homologous series, it differs from the preceding one with a constant group of atoms, which are saying they differ with the methyl group. So that's easy to get. The other characteristics that you also have to keep in mind here is that all of them, they have the same general formula. So for example, if we talk of the general formula for alkanes, the general formula for alkanes, in this case you have alkanes, in this case, sorry, I can't get the eraser. Yeah. So the general formula for alkanes, in this case it is CnH2n plus 2. So we're saying CnH2n plus 2. So this is the general formula for alkanes. Then for all alkenes, we have the general formula looking like CnH2n. Now this simply means this. Where you're seeing the N, in this case, N gives us the number of carbon atoms. So N represents the number of carbon atoms. So in a situation where we have one carbon atom, so how we use this one is that when I have one carbon atom where there's N, I put 1, and everywhere where there's N, I substitute with 1. So there I'll put 1 in the bracket, and then I'll add the 2 plus 2, like that. So I have C1 H 2 times 1, it is 2 plus 2 again here, sorry. So C1H2 plus 1, we have 2. So if we advance there, we're saying C1H2 plus 2, we have 4 here. And then every time we are writing something like this, if it's 1, the number is 1, we don't show it in mathematics. So we say, writing the final answer will look like CH4, and this is the methane. So we are using this general formula to derive the molecular formula of all organic of the homologous series according alkanes. To similar way, we can still derive an alkene with one carbon atom, and in this case, if it is one carbon atom, we might have 1 there, but there is no alkene with one carbon atom, but we start from 2 because we consider certain bonding arrangement. So for this one, you can start with 2 carbon atoms. So if N is, meaning N will be 2, and then so N where there's N, we put 2, so we have 2 times 2, and we get C2. 2 times 2, we have 4, and it looks like this. And we call this one as ethene. So what are we using? We're using the general formula. So we're trying to use the general formula to derive whatever molecular formula that we want to derive from them. So basically that's how we use the general formulas. So we're saying all homologous series, they have the same general formulas. So I've just given the 2 general formulas that we have for alkanes and for alkenes. For alcohols, it is CN H2N plus 1 OH. So there we're saying it is plus 1 OH, that is for alcohols. So just in case you need that, so where there is, if I can just use this side there, we're saying here we are saying it is we're saying for alcohols plus 1 OH. The similar way for acids, we just say plus 1 CN H2N plus 1. Then instead of OH, this time we put COOH. Okay, that's okay. Then that's the general formula we're talking about. And then the other thing that we also have to get here is that all members of a particular homologous series, they have the same functional group. So for as long as we're saying these are alkanes, these are alkenes, we expect them to possess the same functional group. Now the question is, what is the functional group? So we define a functional group as basically group of atoms or bonds that determines the characteristics of a particular atom. So we're looking at an atom or a group of atoms, or rather we're looking at bonds that determines the characteristics of a particular chemical property, or a particular organic compound, homologous series. So if we talk of homologous series called alkenes. For start, the first one, we observe alkenes. So if we can focus on alkenes, you realize to say they have the same chemical properties. I think we talked about this one later. Now, for all alkenes, for them to have the same chemical property, it simply means that they should have the same functional group. Now, in this case, we're saying, what's the functional group that we can give for alkenes? We said it could be an atom or group of atoms, so group of atoms, or rather a bond that is common in any given homologous series, and that's the one that will undergo a particular reaction. So that in this case for alkenes we have no atoms, but we show it by the single bond between carbon to carbon atom. So when you see a single bond there, every time you see single bond, that's the function group for an alkene. For alkenes, we show using the double bond. So for alkenes, we show using the double bond. So the function group for alkenes are just those double bond. So even the way alkenes will react depends on the position of the double bond. Then, if we move further into looking at alcohols, for example. If we move and look into alcohols, we have OH. Now please, that's a function group, and what I show it by doing that. Here I'll show it by that. Here I'll show it with this single bond, double bond. Here saying there's a bond bonded to OH. Then for organic acids, we have COOH. And then for esters, we have COO, like that. So these are the brief function group that I can give. For alkanes, we have a single bond, double bond. For alkenes and alcohols, we have the OH, or rather hydroxy. We have the carboxylic part of that's the COOH, that's for acids, and then we have the bond COO, that is for esters. That's the function groups that I can give for each one of the homologous series that we're going to discuss. And keep in mind, these are not the only homologous series that we have. We might have another one here called alkyne, but in our O-level syllabus we don't look at that, so please take note of that. And then these alkanos are also called alcohols. Where I was using alkanos, these are alcohols. And alkanoic acids, we're saying these are organic acids. So if you might not find this term, but you might find organic acids, don't get confused. Esters are esters, so we'll look at them as we advance. So basically that's the few characteristics that we have every time we try to study and understand a given homologous series. So from today we end on this one. Thank you all for watching. See you next time. Remember to subscribe and share with friends. Thank you.